from pixels to printer dots. In this tutorial, you'll learn how digital images consisting of pixels are converted into photorealistic images printed on paper. It's a remarkable metamorphosis, and if I couldn't see it with my own eyes, I wouldn't believe it was possible. What you'll be learning in this module applies to both grayscale and color images. We'll start with a grayscale image that was output on different black and white printers to establish the basic concepts. Later, we'll extend these concepts to color photos that are printed on color printers. We're looking at a scanned grayscale image of Dr. Terry Downey. This photo appears regularly in my monthly news magazine, The Carillon. Let's examine the image size. The picture measures only 1.18 inches wide by 1.45 inches in height, and its resolution is 200 pixels per inch. Therefore, the image is 236 pixels wide and 290 pixels tall. I'll turn on the rulers in Photoshop. View, Rulers. You see the size of our image here, measured in inches. I'll right-click on the ruler and select Pixels from the list of available options. Now you see the measurements of our image expressed in pixels on the horizontal ruler and on the vertical ruler. When I zoom up to the maximum magnification, 1600%, we see every pixel that makes up this image. I'll zoom out to 600%. We can still see the pixels very easily. There are many different gray tones. Remember, a grayscale file can contain up to 256 shades of gray. Outputting gray shades using black and white printers. Here's the big question. How can a magazine or newspaper printed using only black ink faithfully reproduce all these shades of gray and produce photorealistic results? A standard laser printer uses only one toner cartridge, and it's black. How can this device generate totally convincing grayscale prints using only black toner? Likewise, your home inkjet printer uses black ink for printing grayscale images, and they look great. So what's the secret? How inkjet printers work. The image in the center of the screen is a highly magnified section of Terry's eye. I'll zoom up to show you the individual pixels. You can see many gray tones. When this file is output on an inkjet printer, the natural gray shades are recreated by disseminating microscopic dots of black ink on the paper. We see this here. The output looks speckled because it's greatly magnified. In fact, this small segment of Terry's eye has been enlarged 5,000%. When printed on paper, these dots are invisible to the naked eye, and we perceive natural gray tones in the print. Every printer dot is exactly the same size. They've been dithered in various amounts to create different shades. Light areas of the photo, as we see above Terry's eye, are represented by a sparse density or frequency of dots. Dark areas, like the pupil of the eye and the eyebrow, contain much higher dot frequencies. The process of regulating or modulating the frequency of printed dots is called FM screening. FM stands for frequency modulation. In the industrial printing business, they call it stochastic screening. Almost all inkjet printers operate on the principle of stochastic screening. However, the technique is relatively uncommon for high-end commercial print jobs because of problems controlling dot gain, difficulty in preserving the size of the microscopic dots. With recent advances in printing technology, it's now possible to create printing plates directly from the computer. Companies that have new CTP equipment, computer to plate, are getting great results with stochastic screening. How laser printers work. Standard black and white laser printers are commonly used in home offices and small businesses. Service bureaus use very high-resolution laser printers to output commercial print jobs. Unlike inkjet printers, laser printers output variable-sized black spots on a uniformly spaced geometrical grid. We see this here. Notice the distinct parallel arrangement of black spots. When I zoom up on this segment, magnified 5,000%, we see that the spots are aligned at an angle of 105 degrees relative to vertical. Every black spot falls into a specific location inside a grid. In the printing business, this grid is known as a line screen. We refer to the 105-degree angle as the screen angle. The screen angle is determined by the software that controls the laser printer. Unlike the inkjet printer, where the frequency of equal-sized printer dots is modulated to create light and dark areas, a laser printer creates black spots of various sizes to represent different shades. Small spots are said to have a low amplitude. Large spots have high amplitude. All the spots are located in individual cells within the screen. The printing business refers to this technology as AM screening. AM means amplitude modulation. In other words, tones are created by printing spots of different sizes or amplitude, instead of changing the distribution frequency of a single-sized dot as we had in FM screening. These black clumps of ink are known as halftone spots, and the grid is referred to as a halftone screen. At actual size, this halftone screen contains 100 lines per inch or 100 LPI. We refer to this as the screen ruling. The size of each spot is computed based on the tones of the pixels in the original image. For example, the light areas above and below Terry's eye generate smaller spots. Dark areas, like his pupil and eyebrow, result in much larger spots being computed. In commercial print work, these calculations are made by a raster image processor, or RIP, the brain behind the digital imaging process. The RIP converts the pixels in our image into a form that can be printed by an output device. Two primary types of RIPs are available: hardware and software. A hardware RIP is a dedicated piece of computer equipment usually bundled with a specific output device, typically an image setter. The more modern approach is the software RIP. Here, the imaging software is loaded onto a dedicated server. The server could be any high-end Mac, Windows, or Unix computer. Often, the computer will have multiple processors to expedite the billions of calculations necessary to process an image. I'll zoom up even more so you can see the makeup of these spots. Roughly speaking, the spots are circular in shape. They are comprised of collections of printer dots from the laser printer. Here you see an individual printer dot, the smallest entity that this laser printer can generate. At actual size, this dot measures 1/2400th of an inch. Almost all books and technical documentation refer to the shapes we see here as halftone dots. I make the careful distinction of calling them halftone spots, because each spot is made up of a collection of individual printer dots. In very dark areas, as you see here, the spots are so large that they coalesce and you can't differentiate one from the next. There's an important reason for outputting the spots at an angle. Our eyes are very sensitive to obvious geometric patterns. If the angle was horizontal, we might easily notice the screen pattern in the printed image. Now that you are aware of halftones, pick up a newspaper and see if you can detect the angle of the line screen that was used in printing. There is a desired correlation between the resolution of an image, in pixels per inch, and the optimum spacing for the screen in lines per inch. Typically, the resolution in pixels per inch is twice the resolution of the screen. Our image contains 200 pixels per inch, and the screen is half that at 100 lines per inch. In the next section, you'll discover how halftone spots are computed by the raster image processor based on the original pixels the image contains. How halftone spots are created. Let's explore how halftone spots are created by a laser printer to represent the grayscale pixels we see in our digital image. This is a tiny portion of Terry's photo. We're looking at his left eye. This part of the image measures only 14 pixels across and 10 pixels tall, for a total of 140 pixels. The entire image contains 68,440 pixels. I'm going to enlarge this piece 6,000% so we can see each pixel in extreme detail. Here it is. Count them! 14 pixels across and 10 pixels tall. To simplify our discussion, we're going to make three initial assumptions. Number one, the laser printer's line screen is horizontal. In other words, the line screen runs parallel to the pixels. Number 2. The laser printer's line screen is 100 LPI or 100 lines per inch. 3. The laser printer has a printing resolution of 1200 DPI or 1200 dots per inch. Since the photo has a resolution of 200 pixels per inch, we have 2 pixels for every screen line, both horizontally and vertically. Therefore, each cell in our line screen contains 4 pixels. Some of the cells, such as this one, contain very light pixels. Other cells, like this one, contain very dark pixels. Most of the cells contain a variety of grayscale pixel shades, as you see here. The laser printer will compute the average amount of gray in each cell and then create a halftone spot that represents this amount as a percentage. Our laser printer has a resolution of 1200 dots per inch, and its line screen is 100 lines per inch. This means each cell is 12 printer dots wide by 12 printer dots high. I'm using red squares to represent each printer dot so they'll contrast with the pixels in the background. Of course, in the laser printer, these dots are black. Let's examine this very dark cell on the right side. All 4 pixels in this cell are black. Therefore, to represent these pixels, we need to create a halftone spot that covers 100% of the cell. In other words, we need to fill it with 144 printer dots to create a spot that covers the entire area represented by the cell. There's a very light cell in the top row. All 4 pixels are very light gray, nearly white. For our purposes, I'll say we have about 3% gray density here. To represent this, I need a spot made up of 4 printer dots, since 4 divided by 144 is about 3%. A pure white cell with all 4 pixels being pure white would not require any coverage, and the laser printer would not put any dots into the cell. Here's a cell with 4 light gray pixels, representing about 10% density, and here's its representative halftone spot containing 14 printer dots. This cell has approximately 40% gray coverage and requires 58 printer dots to make up a spot that represents these 4 pixels. Here's a cell with approximately 65% gray coverage. It requires a larger spot consisting of 96 printer dots to represent the 4 dark pixels. You can appreciate that a laser-printed image requires millions to billions of computations to calculate the size of the spots that will be generated for each cell. With the configuration we're showing here, a 1200 DPI laser printer and a 100 LPI screen, we can create 144 different spot shapes. The smallest spot can consist of a single printer dot. The remaining shapes will contain from 2 to 144 dots. Therefore, this laser printer can generate 144 shades of gray plus pure white when the cell is empty and no dot is printed. The formula for calculating the number of shades or gray levels that a laser printer can produce is printer resolution divided by line screen squared plus 1. In our case, we have 1200 divided by 100, that's 12, squared, that's 144, plus 1, for a total of 145 gray levels. A grayscale digital image can contain up to 256 shades of gray. So you can see that a 1200 DPI printer using a 100 LPI screen cannot generate all 256 shades of gray that our digital image contains. Is there anything that can be done to make a laser printer generate all 256 shades of gray? There are 2 solutions, and we'll explore them both. Number 1, use a laser printer with a higher resolution, for example, 2400 DPI. Or, number 2, reduce the number of lines per inch being printed. In other words, use a lower screen ruling. Using a 2400 DPI laser printer. Imagine these pixels are from a high-resolution 300 pixel per inch image that's going to be printed in a high-quality glossy publication. We'll say the line screen for this job is 150 lines per inch. Again, we have 2 pixels for every screen line, both horizontally and vertically, as you see here. Therefore, each halftone cell contains 4 pixels. The big difference is that our laser printer can generate 2400 dots per inch. When we divide 2400 DPI by our screen ruling of 150 LPI, we get cells that are 16 printer dots wide by 16 printer dots tall. A black cell would require 16 by 16 or 256 printer dots. A pure white cell would require none. We can create 256 different halftone spot shapes or leave the cell blank for pure white. So we can now represent all 256 possible levels in a grayscale image. Here you see a 3% halftone spot with 8 printer dots, because 8 divided by 256 equals 3%. This spot represents 10% coverage with 26 printer dots. 26 divided by 256 is approximately 10%. Here's a 40% halftone spot containing 100 printer dots. 100 divided by 256 is approximately 40%. Therefore, a high-resolution 2400 DPI commercial laser printer can generate all the different halftone spots to emulate the 256 gray shades we have in our digital image. Achieving 256 shades with a 1200 DPI laser printer. It's also possible to achieve 256 gray levels using only a 1200 DPI laser printer. To accomplish this, however, we need to reduce the number of lines per inch in our screen ruling. Here you see the original 100 LPI screen with each cell containing 4 pixels and measuring 12 dots wide by 12 dots high. Now you see the same image with a 75 LPI screen. 1200 DPI divided by 75 LPI equals 16 dots per line. Each cell is now larger and measures 16 printer dots wide and 16 printer dots tall. These larger cells cover an area that includes nearly twice as many pixels. The cells are so large that the computed halftone spot may not accurately convey what's in the original image. Look at this cell. The left third is quite light. The middle third is medium gray. And the right third is dark gray. The single computed halftone spot representing this cell would be a medium size and not really reflect the tonal variation occurring across this area of the photo. It's much better when halftone cells are smaller, so they more closely match the pixel shades near to their actual physical positions in the digital image. When this image is printed, the halftone spots will be further apart because the screen contains only 75 lines per inch instead of 100. Although we can now reproduce 256 different halftone spots, representing all our gray levels, the image will appear coarser on the printed page because of the looser spacing of the grid. We refer to this as a low-resolution screen. There's definitely a balancing act going on here. Our 1200 DPI laser printer can give us either 145 shades with a tight screen of 100 LPI, or give us 256 shades with a loose screen of only 75 LPI. What you choose for your job depends on several factors. If you're printing the job on newsprint, a higher resolution ruling of 100 lines per inch is too tight because ink spreads when it touches the absorbent paper, and many of the large spots will coalesce and give the photo a muddy appearance. Printing the job on high-quality paper with only a 75 LPI screen will make the images look rather coarse, and their overall contrast may be compromised because of the large samples computed from each cell. Here are some guidelines for achieving a good combination of screen ruling and obtaining satisfactory shades of gray from halftone spots. A good starting point is to keep the image resolution twice that of the line screen, so an image of 200 pixels per inch will be targeted for a 100 LPI job. An image of 300 pixels per inch would be targeted for a 150 line per inch job. We call this the 2 times rule. When printing on lower quality media, like newsprint, it's adequate to use an image resolution that's only 1.5 times the resolution of the line screen. So a digital photo intended for newsprint at 85 lines per inch does not have to contain 170 pixels per inch. You could get by with 130 to 150 pixels per inch and achieve a desirable result. Higher quality jobs such as annual reports or glossy magazines are typically printed on 133 to 150 LPI screens. For these jobs, it's best to follow the 2 times rule and supply higher resolution images between 250 and 300 pixels per inch. The shape of halftone spots. So far, all the halftone spots I've shown you are symmetrical and more or less round in appearance. They originate from the center of the cell and get progressively bigger until the cell is filled. However, the software, known as PostScript, used in the raster image processor, or RIP, is very sophisticated and can generate spots of almost any shape: ovals, diamonds, triangles, propellers, etc. Round spots can yield uneven blends or gradients when dots become large, filling more than 75% of the cells, and they begin to coalesce. Today, many commercial PostScript devices generate transforming elliptical spots. Small spots are oval-shaped, but around 45% cell coverage, they change shape. First, they become elliptical. Then, in areas of high dot density, instead of a big black spot, the content of the cell is inverted so that a small white oval remains on a black background. The service bureau responsible for outputting your job will have experience printing on different papers using various line screens. They will know how to set up the RIP to give you the best possible results. The goal is to make the spots and the screen angle as inconspicuous to the viewer as possible. Halftone screen angles. As mentioned earlier, halftone screens rarely go in a horizontal direction that is parallel to the pixels, as we see here. Typically, the screen ruling is rotated to an angle, such as 105 degrees, as you saw in Terry's photo. Here's how a 105-degree screen appears over our magnified pixels. This screen still adheres to the 2 times rule because the area inside each cell is exactly 4 square pixels. Halftone spot shapes are computed based on the pixel data inside the cell. In this example, each cell includes all or portions of 9 different pixels. You can appreciate how much math is involved when calculating spot shapes with angled screens. How color images are converted to printer dots. The conversion of grayscale pixels to black printer ink is an amazing transformation, whether we're looking at print output in the form of halftone spots or as stochastic dot patterns. The technology that gets us there is remarkable. Color output is even more profound. Inkjet printers use stochastic screening and dither 4-colored inks, cyan, magenta, yellow, and black, to create photorealistic colors from our RGB images. Higher-end photo quality inkjet printers perform even more amazing magic, juggling 6 to 9 different colored inks. Stochastic screening is gaining support in the commercial print world as well. Most commercial print work is generated using halftone screens. However, instead of requiring a single screen of black spots to recreate a grayscale image, photorealistic colors are generated from 4 separate halftone screens. 4 colors of translucent ink, cyan, magenta, yellow, and black, are applied to the printing paper by 4 individual printing plates. Analyzing CMYK ink contributions. This picture was scanned from a printed copy of my monthly news magazine, The Carillon. You're viewing a CMYK file in Photoshop CS. Remember, Elements does not support the CMYK format. The image has an obvious texture that is particularly noticeable in the blue sky area at the top of the photo. This pattern is the result of the halftone screens that were generated when the picture was printed. From the Window menu, I'll open Photoshop's Channels palette. The Channels palette reveals how much ink color this image contains for cyan, magenta, yellow, and black. Blue sky is primarily made from cyan ink. We can confirm this by examining the cyan color channel. The intensity of the color we see here tells us how much ink will be laid down by the cyan plate during printing. You can see how strong the cyan component is in the sky area. I'll switch to the black channel. The sky is very light, which means there will be no black ink printed in this area. Let's examine the colors that make up the skin tones in the rancher's face. I'll select the cyan channel. The face is very light, meaning little cyan ink will be printed here. Skin tones consist primarily of magenta and yellow ink. When I choose the magenta channel, we see a rich intensity of this color in the rancher's face, so a lot of magenta ink will be printed here. Likewise, when I select the yellow channel, we see a rich color component over the face. There will be a large contribution of yellow ink in this area when the photo is printed. Let's take a much closer look at the rancher's face. This is a highly magnified section of our photograph showing only the rancher's face. We can easily see the screened pattern at this magnification. Let's move in even closer. We'll examine the cyan channel. As expected, there is very little ink contribution in the flesh tones, and the size and density of the halftone spots is sparse. When I choose the magenta channel, we see lots of ink coverage in the facial area, a dense array of large magenta spots. We also see this in the yellow channel. The combination of yellow ink, along with magenta, creates the skin tones in the rancher's face. The black channel contributes little to the face, with the exception of the shadow areas around the rancher's eyes and mouth. Color halftones and screen angles. When a color image is printed, different screen angles are used for each printing plate. If all the screen angles were the same, there would be a very obvious banded pattern in the printed photo. Let's look at the screen angles for each ink color for this photo as it was printed in the Carillon. Can you see the screen angle in the cyan channel? Here it is. Screen angles are measured relative to the vertical direction. This angle is 75 degrees. Here's the magenta screen. Do you see the angle? This is it, 45 degrees. You shouldn't have any difficulty making out the angle in this yellow screen. Here you see it, running horizontally across the image, 90 degrees. There's not too much black in this part of the photo, so you may have some difficulty picking up the angle. Here it is, measuring 105 degrees. All of our screens interact to generate the printed result. We see the black, combined with the yellow, and the magenta, and the cyan, which really brings out the sky in the background. The reason for using an assortment of different screen angles is to generate an overall halftone pattern that isn't obvious to the human eye. With all the screens in place, we see an interesting symmetrical shape throughout our printed photo, known as a rosette. When viewed at normal size, our eyes perceive these circular shapes as continuous tone color, with smooth tonal gradations. Pixels to printer dots. Summary. We've examined how the pixels in our digital photos are converted to printer dots. In the introduction to this tutorial, I said, if I couldn't see it with my own eyes, I wouldn't believe it was possible. By magnifying the dots and spots that we take for granted every day when reading a magazine or newspaper, you've seen the transformation with your own eyes. I trust you're impressed and hope you're convinced by the process and now believe, as I do, that it is possible. My philosophy on terminology. From the outset of this program, I've insisted on being particularly fussy about terminology, especially as it relates to image resolution. Over the years, most of the books and documentation I've read on the subject pay no regard to how the term DPI, or dots per inch, is used. They use the term DPI to describe the resolution of the monitor in digital photos. I insist on using PPI, pixels per inch, since we're looking at picture elements that make up images on the screen. They use the term DPI to describe the resolution of a scanner. I insist on using the term SPI, samples per inch, because a scanner takes discrete measurements as it samples an analog source. They use the term DPI to describe the shapes that exist in a halftone screen. I insist on calling them spots, not dots, because each spot shape consists of an array of printer dots geometrically spaced on a screen that's measured in LPI, lines per inch. They use the term DPI to describe the resolution of a printer. Hey, what do you know? I agree. The tiny dots that are generated by a printing device are properly described in dots per inch. I'm not surprised to see how much confusion there is in the digital imaging industry. If you adopt my philosophy, you'll immediately know the medium we're talking about from the context of the measurement system: PPI, SPI, LPI, and DPI.